forth. We have a function f that is continuous on the interval from 0 to 1, closed interval, except at x is equal to 0.25. We also are given that f of 0 is equal to 1, and f of 1 is equal to 3. And we're going to let capital N be equal to 2. And our job is to sketch two possible graphs of f. One showing, so sketch a function f such that the conclusion to the intermediate value theorem is not satisfied. And then we also want to sketch a function f such that the conclusion to the intermediate value theorem is satisfied. Okay, so just to make sure we're all on the same page, it would be a good idea for us to remind ourselves what the intermediate value theorem says. And so, roughly speaking, you might recall that the intermediate value theorem says that we're going to let f be a continuous function, continuous on the interval from a to b, and we're going to let n be a number between f of a and f of b, and we're not going to allow f of a to be equal to f of b. Then there is a number c in the open interval from a to b such that f of c is equal to capital N. All right, so what we're looking at here is we're asked to graph a function that is not going to be continuous on our interval, okay, not continuous at x equals 0.25, but yet we want our conclusion to be satisfied for one example and then not satisfied in the other example. And so, Andrew, did you have any thoughts on your pictures here?
I just wanted to make sure I did it right.
Okay, so tell us what you did.
Well, like I just drew the first one where I thought that it wouldn't work. I planted the dots first, like where f of 0 equals 1,
Okay.
put that up there.
So f of 0 equals 1, and f of 1 is equal to 3. So we've got those two dots, okay, and our n value is 2. Okay, and we have a discontinuity at x equal to 0.25, so let's mark that in here. Okay, so can you describe your picture that you have on your paper?
Well, like I had the line that goes from 1 to 3.
Okay.
But then on the way up, as it crosses through that 2, I have an open circle.
So an open circle right about here?
Yeah.
Okay, so something that looks kind of like that. Okay, so we've got an example where our endpoints are defined. Our function is continuous from 0 to 1 with the exception of x equal to 2.5. N is equal to 2, that is certainly between f of a and f of b. But there is no x value value for which f of x is equal to 2. Okay? So here's an example. There is no x value, which we'll call c, such that f of c is equal to 2, which is our n. Okay, so this is a totally legitimate picture. Absolutely. Okay, are there questions or comments about that? Okay, so we have an example where we have a non-continuous function, but yet, and it does not satisfy our conclusion. Do you have an example of a picture for where our conclusion is satisfied? We'll start out the same way. So we have 0 and 1, and so f of 0 is equal to 1. F of 1 is equal to 3. N is equal to 2. And we have a discontinuity when x is equal to 0.25.
I just say the same thing, but a continuous line this time.
So you went like this. Okay, so on this one, the only issue with this is that our function that you've drawn is continuous at x equal to 0.25. So what we need is somehow to have a discontinuity when x is equal to 0.25.
Just do an open arrow.
So so let's stick this guy in here. Like that. Okay, so let's take a look. So does this satisfy our conclusion? Is there a number c in our open interval from 0 to 1 such that f of c is equal to n?
Looks like it.
So let's see here. Well, conveniently, my circle is a little bit off, right? So as long as my circle is not directly at 0.25 comma 2, well, yeah, there is an x value, so that probably is, I don't know, 0.3 or something like that.
Sure.
So c is equal to approximately 0.3, and so f of 0.3 is equal to 2, which is our n value. So there is, in fact, an example here where there is an x value such that f of that x value gives us 2, even though our function is not continuous. Okay, so the moral of this story is, if your hypothesis is not satisfied, then we don't know nothing. We can come up with examples of functions that satisfy the conclusion and examples of functions that do not satisfy the conclusion.
Doesn't the theorem say that you can put that any point between 1 and 3 though, and get a, not only a 2?
Right. So the theorem says that for what's embedded in here is for every n, this should work no matter what n you choose.
So it doesn't really satisfy, but just satisfies it at 2.
Right. So in this example here, our conclusion would not be satisfied if we had chosen n equal to 1.75 or something like that. But in this example, we're specifically talking about an n value of 2. All right. Andrew, does that make sense?
Yes.
Okay, cool. Are there other questions about number 34? This is a good question because it was an even one. It's the only intermediate value problem we have.
Could you use because I just drew my picture a little bit different, and I was just wondering if that would still work right. I had just a hole at the 1 at the 0.25.
Okay.
And then I had a dot at the n equals 2, and then just a line, the line's going to the other way.
Okay, so looking something like. Okay, so can you explain that again?
Yep, I had an open hole at the 1. Yeah, right there, exactly.
Like that?
Yep, and then just a line over.
Okay.
And then I had a solid dot at the 0.25 at the 2,
Okay.
and then just a line to the other dot.
All right, so here's an example of a function that is not continuous at x equal to 0.25, but yet, when n is equal to 2, we do in fact have a c value, an x value that f of 0.25 is equal to our n value. And so this is also another good example where the discontinuous function still satisfies our conclusion for n equal to 2. Would not satisfy the conclusion for n equal to 1.5, but does for n equal to 2, which is what they're specifically talking about. Okay, other questions or comments?
So just any function with an open interval on it is still continuous then? So these ones here are both?
These open intervals are continuous. This function is continuous everywhere except at x is equal to 0.25. Does that make sense?
Yeah. Yeah. I mean, I guess I was just thinking that if it satisfies the value theorem, then it has to be continuous throughout the entire function.
In order for the intermediate value theorem to say anything useful, then the hypothesis must be met. If the hypothesis is not met, all that these are saying is that if our hypothesis is not met, then the conclusion may or may not hold. So the validity of the intermediate value theorem, we can't really even apply it and say, well, look, this guy fails the intermediate value theorem. Well, it doesn't fail the intermediate value theorem because it didn't satisfy the hypothesis. What it fails is the conclusion of the intermediate value